Thank you very much. So yes, is the first slide up? Yes, SoK. So science, security, and the elusive goal of security as a scientific pursuit. This is an SoK, so it's large and it's kind of a survey in some sense. So I'm giving a survey of a survey of a survey. It's going to be a little compressed, and I don't have the chance to go through absolutely everything. But selecting, what we think are the highlights from the paper. I mean, over the last, at least decade or so, maybe decade and a half, there seems to have been sort of a desire, particularly among funding agencies in DC, in the US, and in some other countries also, for security to be done in a more scientific way. Part of this may be sort of in response to kind of, somewhat pessimistic views that are occasionally expressed. Every once in a while you dig out kind of salty quotes from, Adi Shamir in 2002 described, non-crypto security as a mess and said it was likely to remain so. Roger Shell described, security as being full of pseudoscience and flying pigs. Any of you young folks in the audience, if you're lucky and you bump into one of the Multics people at the coffee break, they will happily tell you how everything being done here this week was done much, much better decades ago. And that's interesting, but it also contains a kind of a worrisome sign. Well, are we really just not making progress and going in circles? And perhaps in response to that, so principally the NSA and one or two other funding agencies have spun up a science of security initiative where there's a best paper award, and they have some labs that look at this. There was a DoD long JSON report by some kind of worthy, experienced people looking at this, and that's good. I mean, no one disagrees with the end goal of doing security in a more scientific fashion. But what do we mean by science? I mean, everyone thinks that they're doing things in a scientific fashion. I mean, if I want to do things more scientifically, does that mean, more equations, more numbers and graphs, repeatable experiments? What should I do personally in order to make, my work more secure? And so, in writing this survey, one thing, Paul and I definitely did not want to do was kind of set ourselves up as the arbiters of, of what is science and what is not science. We're not going to say, you folks are all doing science and you folks are not. We're not going to set ourselves up, or anyone else as the arbiter of that choice. But we wanted to try to figure out, well, what do other fields mean by this? I mean, we have hard problems. We have, all sorts of difficulties that make our field unique, but so do other things. And, a lot of fields have used science and accomplished, very, very strong things with it. So, believe it or not, in order to kind of try to figure out what we mean by science, we went all the way back to the origin, as it were, and look at the literature of the philosophy of science, and look at, yes, really things like, Immanuel Kant and Karl Popper and J.S. Mill and stuff like that, and also some of the writings of really first-tier, scientists and what they regarded as the scientific method and how they proceeded. And to be honest, it was a lot of fun. I mean, didn't read Kant in the original, but it's actually a lot of fun kind of drilling down on this stuff. To figure out, what we mean by science. I'd ask kind of your patience, both kind of in the talk and, in reading the paper, with some material that might appear at first blush to be, oh, this is kind of philosophical, highfalutin stuff, and, what does it have to do with security? And we'll find out, and kind of, this was kind of one of the surprising things, that neglect of some very basic lessons that a lot of other sciences have taken to heart seems to be at the root of several of the problems that we believe we have in science. So we wanted to figure out, what is the consensus from other fields? And there's a lot of nuance to it. There's a lot of it's kind of, but to reduce it to the simplest kind of statement, and I'm leaving out a lot of detail here, but to reduce it to a very simple statement: if a theory conflicts with observation, it's wrong. That's basically, from physics to biology to chemistry to any other field that you can think of that does things scientifically. That's essentially what they mean. If it conflicts with observation, then it's wrong. And that's really a description not really of how you come up with laws, but it's a description of the feedback mechanism that you apply to them. And it immediately implies one or two very basic things. It implies, well, at least the conflict with observation must be possible. And that kind of says that, well, science must be induction and not deduction, and claims must be falsifiable. So that, refutation is the engine of progress. Self-correction is one of the things that is regarded as sort of one of the defining characteristics of science, and you can't have self-correction unless you've got a way of finding errors. And falsifiability and contact with observation is regarded as the engine self-correction. So induction and deduction. So induction, and this is kind of like, going all the way back to, 200 or 300-year-old philosophical stuff. Induction is statements about the real and observable universe. It's, statements about things you can see and measure and observe. It's, and that leads to scientific statements like penicillin works and the quantum theory and, DNA is a twin spiral and stuff like that. And those kind of knowledge statements are fundamentally different from deductive statements, which is geometry and logic and mathematics and stuff like that. So for example, Pythagoras' theorem and Fermat's last theorem and anything that fits in a strictly logical framework sits very much apart from the inductive framework. And these two differ in a very fundamental way. I mean, the deductive statements, when do we trust a deductive statement? Well, we trust it when we've got a proof of it, not before. When do we trust inductive statements? Well, that's tricky. We don't proceed from axioms. We make observations. We've got to try to figure out how things work. Induction can describe the world, but we never end up with a proof. So how do we trust an inductive statement? And that's where the kind of a lot of the philosophy of science is trying to come up with the criterion. And largely speaking, it's falsifiability. That's what most of the scientific communities have converged upon. And it comes from this guy, Karl Popper, who says a theory that is not refutable by any conceivable event is non-scientific. That if you can't refute something, if you can't bring it into contact with observation, if there's no possible way of showing it wrong, then really it can't be regarded as a scientific statement. And there's a very simple reason. It's, if your claim can't be falsified by any observation, then it's consistent with every observation. And if it's consistent with every observation, then nothing observable depends on that claim you've made. Here's the set of observable things in the universe. Here's the claim you've made. They're non-overlapping. There's no possibility that you're affecting. So that's largely speaking at a compressed version of a compressed version of our criterion. We have deduction and induction. Deduction stuff is great, but you don't. You can't describe the real world. You can have proofs, but you can't describe the real world. Inductive statements, they describe the real world, but when do we believe them? Only when you've tried to falsify and failed. That's the criterion that we apply to trust an inductive statement. So wait a second. So math isn't science? Well, actually, yes, in this definition, math is not science. That is to say, no observation contradicts Pythagoras' theorem. If we start from axioms and then we derive the logical consequences of those axioms. If, for example, we go back and we measure the door and we find that a squared plus b squared is not equal to c squared, we don't say that Pythagoras is wrong, we say that the door does not satisfy the axioms. So an axiom is something like parallel lines meet at infinity. It's not even meaningful to talk about whether it's true or not true. It's simply the exercise of mathematics is to discover the logical consequences of your axioms. And those are fundamentally different from finding the logical consequences of your assumptions, which, for example, an attacker can't do a log in a finite field. We always have the remaining uncertainty, well, maybe he can, and if one day he does, then it changes everything that we believe in all our downstream consequences. Here's the main point. Whether a real-world system actually satisfies a set of assumptions is an empirical claim. It's not a deductive claim, and it can only be tested empirically. And as we just said, empirical claims are tested how? By trying to falsify them and failing. And that's only then do you have faith that they can be believed. So reasonableness of assumptions is something that people often fall into and kind of think, well, I've got a bunch of assumptions and I'm going to, my assumptions are reasonable and therefore this is a way of pursuing the truth. This is, so Newton, for example, says that in a vacuum, the speed of a falling body is going to be g times t. Now, we don't decide whether we trust Newton by going outside and measuring the air pressure. We realize that the assumptions of the model are not met. We trust it because it has accurate predictions and for no other reason. Reasonableness of assumptions. I mean, every set of assumptions departs from reality in one respect or other, and deciding which departures from reality are okay is largely subjective. So then, that's the summary of the summary of the summary is, deduction can reveal to you the tautological consequences of your assumptions, but has no tools to help you decide whether those assumptions actually match reality. That is an inductive claim and has to be, pursued empirically. Okay, you could be forgiven for thinking at this point, well, that's all very fascinating. What does any of this have to do with security? And so this is where, somewhat to our surprise, we kind of found that neglect of some of these questions have actually are at the root of some of the problems that we seem to have. So so security, so one of the consequences of this inductive-deductive split is that, deduction, traffics in uncertainty, but science certainly does not. And in security, we often have a kind of a search for certainty or search for guarantees in the sense that we even have folk theorems around it that says that, security is only as good as the weakest link, and, unless you have something that's absolutely guaranteed, it's absolutely worthless. And that's a tempting line of inquiry, but if you actually pursue that, it seems to lead, into all sorts of, it leads you into all sorts of problems. So here's an example of a problematic claim, and this is sort of one of many samples that we kind of extract from the literature, which says that there is no and cannot be any empirical evidence for the security of design. The only way to do it is with a formal mathematical model, and the only way to get certainty, and we really want certainty when we talk about security, is to do so mathematically. And that's kind of a true statement, but there's a problem with the statement, which is that, well, you're making a formal guaranteed statement, but about a mathematical system, not about a real-world system. So if you look at the diagram here, we have a mathematical system, A prime, and that we can prove all sorts of strong things and rigorous things about it. Unfortunately, however, that system doesn't have a power supply and it doesn't have a keyboard, and no one can ever use it, and no one can enjoy those guarantees that you're giving. What we have to do is implement some version of that on a real-world system. And that real-world system, well, what connects the formal system to the real-world system? It's assumptions. And remember what we were saying, that we can only test the assumptions empirically. This is not something you can't deduce whether the real world actually satisfies the model that you have of it. So in other words, we have a formal system A prime. What do we have for our formal system? We have a proof. What do we have for the real world system? We have a proof plus an English paragraph arguing that our assumptions match reality. But a proof plus a paragraph arguing that your assumptions match reality is not a proof. It's and whether your assumptions really do can only be tested empirically. So an example of this working well is something like, well, if we claim that in attack on SSL, you must solve a hard crypto problem, and then we figure out by attacking that assumption that no remote timing attacks are actually practical. But if you compare this formal system and the real world system, you will find that the claim that a real-world system, enjoys the same properties as the formal system A prime. It is assumed, not proved, and it is actually, there's no possible proof that will ever show that this to be the case. There's no possibility of ever showing that A is going to be immune to attack. This is simply, it's equivalent to trying to design perpetual motion machines. This is something that is simply not provable. And the result of this, and it seems to be a problem that it keeps occurring in the literature, is that there's no end run around the messiness of dealing with the real world and dealing with how well your models match reality. This is not something that can be somehow circumvented by doing things sufficiently formally. You have a set of assumptions on how your model matches reality, and this can only be tested empirically. A proof plus an argument that assumptions are reasonable is not a proof. But there's a real danger that it's not going to be a scientific statement either, because unless the assumptions have been subjected to vigorous attempts at refutation, it's not a scientific statement either. Now, this problem doesn't seem to just crop up in kind of examination of formal stuff. The failure to bring theory into contact with observation is, it occurs it's sort of a running story throughout much of the literature that we surveyed, kind of on attempts to do security scientifically. Here's a very basic example from a Morris and Thompson paper, decades ago, saying, well, passwords should contain a mixture of upper, lower, and special characters. And this was, this is the origin essentially of this particular claim. The assumption, the theory behind this, was that forcing people to choose things this way would enforce people to choose somewhat random strings rather than the common English words that they were using. Well, we went essentially 3 decades assuming that this was the case, but without ever checking the validity of this assumption, or without ever trying to falsify it. And we all know how this worked out when eventually we do bring it into contact with reality. Now, this is it's a very simple, basic example from passwords, but it's not this story is repeated across many places. So if you look at a lot of the stuff that we have in usable security, a lot of these claims about passwords and passwords should be changed every 90 days. Well, what is the origin of this claim? Does it come from A/B tests? Did we do a longitudinal A/B test? No, we did not. Have we looked at the varying experiences between people who did things one way and did things another and looked at the difference in outcomes? No, we didn't. What actually happened is that we had a set of assumptions which we failed to bring into contact with reality and did not test kind of the way they should have been tested. So just, I'm about to, I think the timer started a little late, by the way. It started but reliance on implicit assumptions. This is one, let me sort of, more or less end on this. It's like reliance on implicit assumptions. This is, almost everyone in the room will pound the table and insist how important it is that our assumptions be articulated in an extremely, precise way. So for example, if you look at the claim, changing passwords every 90 days improves outcomes. Do we know what the assumptions behind this are? One of the values of falsifiability is that it allows you to root out implicit assumptions in your, so if you claim under certain assumptions, this improves outcomes, well, can you describe the evidence that would prove this claim false? If you can't describe the evidence would prove the claim that changing passwords every 90 days improves outcomes, it means that you've got implicit assumptions in there that you really don't understand. You have to tease out one by one. And it's, which is, okay, so if we can't describe the evidence that would refute that changing passwords every 90 days improves outcomes, or that choosing stronger passwords improves outcomes, we've got implicit assumptions. And here's why that's important. Well, if we don't understand and can't list precisely what the assumptions are, it's very hard to make the argument that we have subjected those assumptions to the only scientific test that matters, which is at rigorous attempts at refutation. It's hard to say that we've done that if we can't even list what those assumptions are. And basically, that is the problem, is that we don't have mathematical support for many of these statements. But we don't have scientific support either. The only scientific support that counts, which is putting your assumptions to rigorous attempts at refutation. I'm going to skip to just the last concluding point that we had out of this is that, doing science is hard. I mean, it's a set of constraints. And we kind of tried to summarize a lot of our findings in the one of the things that comes up a lot when people discuss science of security is people are very good at saying, well, security is different. Security has an active adversary. We don't have natural laws. We're dealing with man-made artifacts and things like that. And well, there's very little support, if you look at the philosophy of science, for saying that, well, exemptions are allowed and we can allow ourselves to do things in a different way. Science isn't really applicable just in rare circumstances. If you go look at the things people have done with it, it's kind of just amazing. Science is really just the best way that we know of making inferences from what we've seen to things that we have not yet seen. And it's basically this falsifiability that brings in the feedback mechanism that gives self-correction. If you decide that it's not appropriate, well, deciding that it's not appropriate without having something to replace it with effectively gives up on the self-correction and means that you can stay stuck in the same state for a long time without ever correcting your errors. Okay, I'm done. Thank you.
All right, so thanks, Cormac, for this very thought-provoking presentation. If maybe we have time for one or two questions. So go ahead.
Hey, great talk. Stefan Savage, UC San Diego. So I'm curious, so I agree with everything that you've said, but I'm curious in particular how you address the issue of things that we wish to measure empirically which are changing out from under us. And that largely has to do with the fact that we have people using these computers, and they change the way they behave over time in the same way that while polling may use the scientific method, which candidate they like changes from time to time. So how do you refute something where, in fact, from one decade to the next, in fact, things may be totally different?
It is extremely hard, right? And one of the things that people find attractive and kind of practice all your ideas on the philosophy of science around physics is it seems to have these invariant laws that go on from the beginning of time until the end. But the fact that that we don't necessarily have invariant laws and things are changing out from under us, I mean, that is a difficulty, and it really makes things very. There's no. there's no easy answer, but the fact that it's hard and things change a lot does not give you an excuse slip to come up with other mechanisms that say, I will invent scenarios about what attackers can and cannot do and substitute those for bringing theories into contact with observation. I guess our main point is that for a lot of the things, we've acted on many things where, yes, measuring them would be hard and they change under you all of the time, but assuming, for example, back with that Morrison-Thompson paper in 1979, that things would remain the way they were for decade after decade, that was a bad assumption. The fact that it's changing is a difficulty, yes, but that still doesn't excuse you from remeasuring as often as you have to if that's the only way things can be done.
Hi, Seda Gurses from Leuven and Princeton. Thank you so much for the paper.
Sure.
I have a question with respect to its somewhat positivist slant. In the contents of the bigger paper, you have actually looked at some of the qualitative studies, but I'm wondering, what do you think of the role of philosophy in security, since that's kind of the premise of your paper, which is not scientific, but which is very much about questioning our assumptions? And second, what is the role of engineering, since it is so instrumental to instrumenting and doing science and doing the observations you're talking about? Thanks.
Okay. So it is positivist in the sense that, I mean, there is, philosophy of science has continued long after Popper, and many of there's been much new stuff, largely speaking, which we don't kind of pay that much attention to. I think the positivist slant kind of comes largely from, there's been a bunch of stuff in philosophy of science in the last couple of decades that if you look at people like, front rank scientists like Feynman, they largely speaking ignore those developments. I'm not saying whether that's a good idea or a bad idea, but largely speaking, we're sort of, going with what the consensus of the community was. Engineering versus science, and I do agree, I think there's a very important point, and it goes back to the point that Stefan asked also, is that engineering is such a huge part of what we do. And you wouldn't accuse, say, the people who did Unix for doing things non-scientifically for, they built an artifact. They didn't start with, deriving the laws of operating systems and then build, this thing. They built this artifact, put it out there. And then, but saying things are just engineering is the approach that Popper and positivists take to describing science. It doesn't describe how you come up with laws. It describes the feedback mechanism that you provide to them. And I think the same thing is true with engineering. We do a lot of engineering. What's important is that you have a feedback mechanism. And for things like operating systems that are in use every day, there was a feedback mechanism that, that said Unix would succeed and many other things would fall away. It's the absence of a feedback mechanism that takes some of the silly stuff that we did around passwords and said, these are sensible things and these are not sensible things. Engineering on its own doesn't get you there if you just engineer things at random. What you need is, a mechanism that sorts out the sensible things from the non-sensible things. Often that's the market, but in security, I guess we need kind of something additional. Okay, thank you.
Let's thank the speaker again.